Now that you have seen a lot of examples of different chemical reactions and you practiced balancing them, now our goal is actually going to be able to predict the products of reactions just by seeing what the reactants are. It is totally impossible to memorize every single chemical reaction out there. There's way too many. But what's neat is we can classify them into one of 5 categories, generally speaking. And those 5 categories are combustion, synthesis, decomposition, single replacement, and double replacement. We're going to go through each of these in detail in the future. Right now we're just going to do a quick overview of all of them so that you can look at a reaction, and based on its reactants, you should be able to identify what kind of reaction it is, even if you're not able to predict the products quite yet. So that's going to be the key right there, is to look at the reactants. And that should be able to give you all the information that you need to classify as one of the 5 reaction types. So the first one is probably the most easily recognizable, and that is a combustion reaction, which is exactly what it sounds like. It's something blowing up. Technically, however, it's something that reacts with oxygen. Now this can be lots of things reacting with oxygen. The most common way you are going to see it is as a hydrocarbon reacting with oxygen. So a hydrocarbon is something that contains carbon and hydrogen in some ratio. It might also contain oxygen or nitrogen, a couple other elements, but at its base definition, a hydrocarbon just contains a lot of carbon and a lot of hydrogen in some ratio. So if I were to write an example of a combustion reaction, one would be C5H12, which is pentane, by the way. Okay, so there's my hydrocarbon, reacts with oxygen, so plus O2. All right. When you have this kind of combustion reaction where you have a hydrocarbon burning with oxygen, your products are almost always going to be carbon dioxide and water. So yeah, I said look at the reactants. If you have a whole combustion reaction written out and you see carbon dioxide and water as products, I mean, that's a pretty good giveaway as well. Of course, this reaction is not balanced. I'm not going to worry about phases today. In order to balance this, we've got 5 carbons here, so we need 5 carbon dioxides. There's 12 hydrogens, so I need 6 waters to compensate for that. That gives me 10 plus another 6. Oxygen's on the right-hand side, so I need 8 oxygen molecules. Okay, so that's a combustion reaction. A lot of them look exactly like that. This is an example of complete combustion. All right, just as a side note there, we will also talk about incomplete combustion, but we'll save that for later. Synthesis is the second kind of reaction, and to synthesize means to put together or to make. So that's a good thing to remember when you're trying to recall what the pattern looks like. So with a synthesis reaction, usually it's 2 elements, but it can be 2 compounds or one of each that combine to make, and this is the important part, they form one product. Okay, so the hallmark of a synthesis reaction is that you only have one product. Now, if you have 2 elements reacting, the only thing that they can do is make one product, right? So, for example, we can keep it really simple. We can just make salt by combining sodium and chlorine. Remember, even though this is bonded, this is still elemental, so this still fits into this category right here. And that's just going to make NaOH1 plus ClH1 minus NaCl. Okay, and yeah, we can balance it. So that's an example of a synthesis reaction of 2 elements. So again, what I was trying to say is the only thing these 2 things can do is just combine to make one compound. Another example would be reacting water with sulfur trioxide, which would make sulfuric acid. Okay, this is how a lot of acids are made. All right, and that's an example of 2 compounds synthesizing to make one product. Again, this is the one, the 2 elements, that's the one we're going to go over more often or see more often. Okay, these 2 are opposites of each other if you think about it in terms of pattern. Synthesis is making one product, decomposition is taking one reactant. All right, so this is probably I know I said combustion was easy to identify. Decomposition, I'd say, is even easier, because if you just see one thing and then a reaction arrow, the only thing it can do is decompose. So one reactant compound breaks down to form 2 or more products. Okay, so here's a couple examples of that happening. And again, right now, I'm not worried about you being able to do this. I'm worried about you being able to look at the reaction and identify it as that reaction type based on the patterns. So decomposition, if you saw something like this, if you had magnesium oxide and then just an arrow, well, that magnesium oxide isn't reacting with anything else. So the only thing that it can do is decompose or break apart, and that's the only change you can go through. Usually decomposition is aided on by either UV light or some heat, okay, something like that, to cause this decomposition to happen. Sometimes it's just a spontaneous reaction. So this would break down and form its elements. So magnesium and then oxygen. And of course, oxygen is diatomic, so it'd have to be O2. So to balance this, I'd need 2 magnesium oxides and 2 magnesiums. Now this is called a binary decomposition, because the reactant itself is a binary compound, meaning it only has 2 elements. Another example of a decomposition reaction would be with a compound like this, something that has a polyatomic ion in it typically. So this is sodium carbonate, and sodium carbonate is going to break down or decompose into sodium oxide and carbon dioxide. Again, I don't need you to be able to predict that right now. Just be able to look at this pattern and go, oh look, I've got one thing breaking down into 2 or more things. It must be decomposition. So this compound right here has 1, 2, 3 different kinds of elements. That makes it a ternary decomposition reaction. And that will be important to note later. So we've got 3 so far, and now we get into our replacement reactions. So there's 2 different kinds of replacement reactions. There's a single, and then there's a double. Okay? And the way that you distinguish between them, again, it comes back to the reactants. So in a single replacement reaction, you have an element reacting with a compound. In a double replacement reaction, you have 2 compounds that are reacting with each other. Okay, so that's how you're going to differentiate between the 2 of them. A couple of examples of a single replacement reaction would look something like this. So again, that hallmark we're looking for is an element reacting with a compound. We could do sodium and silver nitrate. Okay, so even before I write the products, you can look at that and go, oh look, element, compound, must be single replacement. So that's the pattern of reaction that's going to follow. So what happens here, and again we'll go over this more later, the sodium replaces the silver, right? We see that word replacement. So this is called a metal replacement. So sodium ends up in the compound, we make NaNO3, and silver gets kicked out all by itself. This reaction is already balanced, but I'm going to make a note here. This is called a metal replacement. The sodium replaces the metal in the compound, since sodium is metallic itself. You can probably guess that we're also going to have the opposite example, which would be a non-metal replacement. Here's an example of that. We could have lithium chloride reacting with fluorine gas. Okay, so again, compound reacting with an element. This time the fluorine is going to kick out the non-metal, right? It wouldn't make sense to have chlorine and fluorine bonded in an ionic compound. So we're going to make LiF and then Cl2. Okay, this one does need to be balanced. 2 of those and 2 of those. So this would be your non-metal replacement. Okay, which, pardon me, leaves me with our last classification or type of chemical reaction, and that is double replacement. Again, identifiable because you have 2 ionic compounds that are serving as your reactants. They exchange ions and form 2 new compounds. It's important to note here that phases are a vital part of this reaction and actually go to determining whether or not the reaction happens. Single replacement has a thing like that too. We'll talk about this later, but single replacement depends on the activity series. Double replacement is dependent on what we call solubility. Okay, so just a heads up there. Here are a couple examples of double replacement. We could have, I don't know why, but I really like silver right now, so AgClO3, let's do silver chlorate, reacting with sodium sulfate. Again, two ionic compounds. All right. We go through a double replacement. It means that they exchange their ions. So silver is no longer going to be bonded to the chlorate. It's going to be bonded to the sulfate, not to the sodium. You wouldn't have two metals bonded to each other. So this would be Ag2SO4. And then we're also going to make sodium chlorate, so NaClO3. All right, then I'd go back and balance this thing. It'd look like that. As I alluded to here, the phases are very important. We will talk about how you can determine this later, but I know that silver chlorate and sodium sulfate are both aqueous compounds. Sodium chlorate is also aqueous. So, silver sulfate is actually a solid precipitate that would fall out of this reaction. All right, and that's the reason that the reaction progresses at all. Here's another example. If we have H3PO4, which is phosphoric acid, and let's say that it reacts with sodium hydroxide, which is a base. So we have an acid and a base reacting. We know that they neutralize, they make a salt. In this case, it's going to be sodium phosphate. And then the hydrogen and the hydroxide ions will react and form water. Okay. In terms of balancing, we need 3 sodium hydroxides to make this happen. And we'll also produce 3 water molecules. In terms of phases, I've told you that acids are always aqueous. Okay. Sodium hydroxide is also aqueous. You don't need to know this right now. I'm just telling you sodium phosphate is aqueous. And you should know that water is a liquid. Okay, so notice on our reactant side, we always have 2 aqueous things. I'm going to retract that statement. We almost always have 2 aqueous things. On the product side, you need to have at least one thing that is not aqueous for the reaction to happen. So for this first example, it was the silver sulfate, which was in the solid phase. In the second example, the water qualifies because it was liquid and not aqueous. So you're creating something that falls out of the reaction that's no longer dissolved in the solution. And this right here is an example of an acid-base reaction. Okay, so just by looking at those patterns, that should be enough to visually assess a reaction and know what kind of reaction it is or what type of reaction it is, even if you're not quite able to predict the products as of yet.